Okay, quick example on projectile motion here then. I showed you an example in the lecture, and this is linked on the Canvas pages as well, and I'll put it in the video description for this too. Of this little cart, which has this kind of launcher here. So there's this cannon, which is going to launch the cannonball vertically upwards while this cannon is moving in the horizontal direction. And this is an example to kind of prove that the horizontal and vertical motions are independent of each other. Because, of course, what we saw in the video was that when this thing moves over to here, the ball follows a trajectory where it actually reappears exactly at the right moment to kind of drop back down into exactly into the cannon where it was. So basically, as this ball is moving vertically upwards, it's kind of following this trajectory because it has some initial velocity in this direction as well. But of course, the cart is moving underneath it at exactly the same speed, and we see the ball reappear at exactly the right moment to kind of go back down into the little launcher there. So we saw a video of it, but let's now solve a problem with some numbers in. So if the cart moves at 2 meters per second, which is pretty fast, and the ball is launched at 5 meters per second, vertically, of course, it's launched straight upwards. Calculate the max height, first of all. So how high does the ball get before it begins to come down again? And then also the distance traveled by the cart while the ball is airborne. Okay, so let's get about solving this then. So we're told that our initial velocity is given by, so our velocity initially, well, we have a horizontal component of 2 meters per second and a vertical component of 5 meters per second. So the velocity can be written in component form, 2I plus 5j meters per second. That's our velocity. And we are going to set about trying to solve the Suvat equations for this motion. And in order to do that, we need to think a bit carefully about what else we know. So we're asked to find the displacement. So that's something which we don't know yet. We don't know the time because, again, it doesn't say in the question anything about time. We don't necessarily know what the final velocity is. So that will be our v. So if you think about this as our u, our initial velocity. What's our final velocity? We're going to come back to that in a second. The acceleration we always know in these problems is just given by minus gj. Okay, that's just the acceleration due to gravity. And of course, that's in units of meters per second squared. The final velocity, well, for what's going on here, the cart moves at a constant speed. So the horizontal motion, this never changes. There's no acceleration acting in the x direction. So we know that the I component, or the component in the horizontal direction, is always going to be 2 meters per second. So the final velocity will have this 2I in it. What about the final velocity? Well, let's think about just this first part of the motion first of all. The ball reaches its maximum height here in the middle. When it reaches that maximum height, it's no longer moving upwards, and it's just about to start moving downwards. So the vertical component of the velocity, basically the ball is moving upwards up until this point, and then it's moving downwards. Well, that means that at this moment in time, this vertical velocity must be equal to 0. And this is a standard thing that we need to know about these projectile questions. When you're at your maximum height, your velocity component in the y direction is equal to 0. So for this initial part of the problem that we need to solve, this is the y component of our velocity. It's 0j meters per second. And so now we can go about attempting to solve this problem. So in order to do that, let's first of all calculate what's the time taken to get to this point in the motion. So let's do that with v equals u plus at, because that then will give us everything we want. So we will have our 2I plus 0j meters per second, that's our v, equal to our initial velocity, that's 2I plus 5j meters per second, plus the acceleration, so that's going to be minus gj meters per second squared times the time. Okay, so just to make clear, the Suvat equation we're using here is v equals u plus at. Okay, and the time, of course, is in units of seconds. So, and we just check that our units match out here. We've got meters per second on the left-hand side. This is in meters per second. And of course, this will cancel with that, and we'll end up with meters per second as well. So everything checks out there. So just filling this in then. So we'll get 2I plus 0j meters per second equals to 2I plus, and then the j component here will be 5 minus g times the time, j meters per second. All right, so you could have done this with the separate components. I just wanted to show an example where we do this at the same time. But now what we can do is we can look at the two components individually, just equate the I part and the j part. So clearly 2I and 2I, everything's fine there, that all checks out. What we're looking for is how we've got 0 here on the left-hand side and 5 minus gt on the right-hand side. So solving that then to find the time, we have 5 minus gt equal to 0. Of course, this implies that the time is equal to 5 divided by g seconds. Okay, so that's our time. And if you want to plug some numbers in there, you'll get that this is about 0.51 seconds. All right, so that's the time it takes to get to the apex, but that's not what we're asked. We're asked what the maximum height is. So in order to determine the maximum height, we need to now substitute this expression in to another one of our Suvat equations to determine the displacement at that moment in time. So what we're going to do is substitute that in to our s equals ut plus a half at squared. And so we'll have that our final displacement is equal to our initial velocity. So our u, again, remember, is 5 meters per second in the I direction. Sorry, I've said that wrong. It's 2 meters per second in the x direction. So 2I plus 5j, that's our initial velocity, times time, which I'm going to write just in this form, so 5 over g, just so I'm not messing about with decimals. So that's ut plus a half at squared, so a half, again, minus gj times our time, which is 5 over g squared. Okay, and I mean, I haven't written the units out in this one, but you can just check. This displacement should be in units of meters. This is a velocity, so this is meters per second. This is time, so this is seconds. So the seconds cancel out, and I end up with meters here. And here I have an acceleration, which is in units of meters per second squared. And here I'm going to have meters per second squared. Sorry, this is in units of time, so this would be seconds squared. So the meters per second squared cancels with the second squared here, and I just end up with meters. So everything checks out for our units. Okay, so what's this going to be then? So we'll have our s equal to, well, we'll get 10 over g I plus 25 over g j plus, well, what do we get from over here? We're going to get minus g over 2 times 25 over g squared j. Okay, and then we can just plug the numbers in again. So I was just keeping this just to make sure you're following along with the algebra. But once you actually start plugging the numbers in here, we still just end up with 10 over g I, which is roughly 1 point something. And for the j component, we end up with, well, this works out at sort of 25 over 19.6, which is 2g. And that's our j component, and this gives us, just check my numbers, 10 divided by 9.8 is 1.02 I plus 1.3 j meters. So Remember what we were doing here, we were finding the time at which it kind of reaches its maximum height. So going back to our diagram here, we found the displacement of the ball. So our ball started here, kind of think of this as our origin. And at this specific time, we have found that the displacement is given by this expression. It's 1.02i, so it's near makes it for 1i plus 1.3j. So the question asks us what the maximum height was. Well, it's just this maximum height is 1.3 meters. Okay, that's the answer to that first part. The second part of the question then is the time at which the ball falls back into the cannon again. And what we can do to solve this is basically just to plug in our final displacement. And we know that the final displacement in the vertical direction will be 0, because we start at a displacement, we start at this position of 0, and we end at this height. Sorry, we start at a height of 0 and we end at a height of 0. So basically we're finding the range of this parabolic motion. So we can plug that in and find the time if we wish. And in fact, I encourage you to do that as an exercise. Just imagine that we didn't solve this first part and just solve for the vertical motion. Find what the time is, or sorry, the distance traveled by the cart. So find the x component of sorry, I'm messing up what I'm saying here. You find the time at which it comes back down to the ground, and then plug that in to the final to the expression for the position to determine what the range is. We're going to take a shortcut here, which is that we know that this motion is symmetrical. Okay, we're not taking account of wind resistance or anything like that. So basically what that means is that this first part of the motion, up until this point where we reach the maximum height, is going to take exactly half the time that it takes us to get to this final position. So as a shortcut, we're going to just jump straight to the fact that the final time, so basically using what we did in the first part, the final time must be equal to, well, it's twice this 5 over g seconds. So it's roughly equal to, it's 10 over g, sorry, it's exactly equal to 10 over g. Which again is this 1.02 sorry, it's seconds, it's a time. Okay, so that's the time at which it comes back down again. And we can plug that into our expression for the position to determine how far it's traveled. So again, we have our position S, that's going to be equal to ut, so that's 2i plus 5j times the time, which is this 1.02 seconds. I'm going to leave the units out of this expression just because it's getting a bit messy. So that's our ut plus a half times the acceleration. Again, the acceleration is just minus gj. So that's our half a t squared. So we get 1.02 squared. So again, this is just s equals ut plus a half a t squared. That's what we've done here. And I realize I've made that kind of messy. So let's just write that out again. So that's just s equals ut plus a half a t squared. That's all we've done here. Okay, and what we want to determine basically is the range of this motion. So that's the x component of this position. So let's just multiply out the numbers. We're going to get 2.04i plus 5.1j, and then we're going to get a half g times 1.02, well, 1.02 squared. So when I multiply all of that out, what am I going to get? Well, I get 4.9 times 1.02 squared. 1.02 squared, just typing that into my calculator, is 1.04. So, and then multiply that by 4.9, and I will get 5.098. Don't really need that many decimal places, and there should be a minus sign there as well. It's got a minus sign here, so minus 5.1, let's say. Minus 5.1 j. And of course, I should have expected that basically these two components will cancel out. And the reason I should have expected that is, of course, when I come back down, my vertical component is 0. So these two components cancel out. And what I'm left with is that my final position is at 2.04 I, because these j components cancel out. In other words, the cart has traveled to 2 meters to one decimal place. So that's the way we solve this. So in this example, I was trying to keep all of the components together, and rather than solving the horizontal and vertical motion separately. You are, of course, free to do that if you prefer that. I just wanted to give a counter example, because every other example we've done, we've solved this separately. But that's how we go about solving these kinds of projectile motion problems.